please join me in welcoming Professor Myles Allen.
Thank you. Thank you very much indeed, and again a hearty welcome to those who are new, who have come along specifically to this lecture, and actually for me an even bigger welcome to those familiar faces I'm seeing and have been seeing over the past 3 years. It's amazing to think that this is the penultimate of my series of Gresham lectures. This is number 17 in the series of 18, and we're coming to the big questions last. I mean, that was partly by design, but also I'm realizing that it's all packing up towards the end, because these are the questions that people really are struggling with at the moment, and there's nothing that I've done in my research career that has actually sort of landed me in hotter water than, and you might be surprised to hear about this, because I got in fairly hot water on some other topics that I've talked about in these lectures, but when we ventured into the question of how you measure the impact of agriculture, particularly livestock agriculture, on climate in general, and what that means for the future of livestock agriculture in a net zero world, which is what I'll be talking about here. And I've already given away the punchline in the rubric in the summary of the talk. So, the very short answer to the question we're asking ourselves is no. A slightly longer answer is, well, perhaps, or at least livestock agriculture as we know it. So if there are any farmers watching online, you're extremely welcome, and thank you for joining us. But don't just sort of stop listening as soon as I say no. Bear with me. There is more to this. And then the even longer answer is of course, it depends, and it depends importantly on how we define net zero, which is where I come into the story. I don't really have much to say about the rights and wrongs of livestock agriculture other than helping people understand what the implications are of different sectors on global temperature. And the final thing is whether we want to fight about it. And lots of people do seem to want to fight about it. A few years ago, this was the sort of message that everybody's given. The number one cause of climate change is animal agriculture. Lewis Hamilton muscled in on this. Go vegan. It's the only way to truly save our planet today. Wearing his Formula One jacket. It can be done so quickly. All you have to do is put your mind to it. Okay, well, thanks, Lewis. And then, of course, we have UK farmers now getting increasingly agitated about this. Demonstrations just in the past few months. Net zero means no food. End the net zero madness. It's worryingly, even politicians seem to be relishing a fight over net zero, although Ed Miliband here was talking about energy policy. There's other politicians who really seem to be rubbing their hands about maybe not so much in the UK, but in other parts of the world, about sort of taking on the farmers. And one of the things I really am concerned about is I don't think this is a fight we need to have. That's the main, there's many fights being picked in the world. There's probably a big fight we do need to have, which I'll be talking about in the final lecture, about what we do about fossil fuels and about the responsibilities of fossil fuel companies. But I don't think the big fight with agriculture is one we need to pick right now. Or indeed, I think we can achieve our climate goals without that fight. So what have I got to say about this? I mean, it's important just because I work on climate change. That doesn't entitle me to a privileged opinion on something like whether or not you should be a vegetarian. And so I think it's really important. Physicists are a little bit inclined to think because they're good at one thing, they must be entitled to an opinion on lots of other things. So I should be clear what I can talk to you about and what I can't. I'm no expert, absolutely no expert in agriculture in general, in soil management, in all the many sort of difficult decisions that farmers have to make all the time. What I do know about is greenhouse gases. That is what and all of the lectures to date have been about carbon dioxide. And I've occasionally mentioned the other greenhouse gases that we worry about. But I've kept on saying, yes, but carbon dioxide's the important one, so we're now going to go back to having mentioned methane and nitrous oxide, we're now going to go back to carbon dioxide. And globally, if we look at emissions over the past century, and that little excluding land use change means these are just sort of direct emissions from human activity rather than the impact of deforestation thrown in, you'll see that globally, carbon dioxide is the biggest source of emissions in the way we conventionally compare emissions. And you'll see, but methane and nitrous oxide, the blue and the green lines, are sort of in second and third place. We'll get on to more detail about how we compare greenhouse gases and so on in the course of the lecture. But if I just blow this up by a factor of 10 and show you the impact of agricultural emissions, the main message of this figure is the lines are reversed. Carbon dioxide's down the bottom. If crucially, we are excluding land use change here, so this doesn't include the impact of deforestation, but in terms of direct emissions, carbon dioxide's down at the bottom because agriculture doesn't use that much. It uses a certain amount of fuel for driving tractors and so forth. But by and large, most of the emissions coming out of agriculture are nitrous oxide, which is generated by manure, but fertilizer in general, artificial fertilizers in particular, and the blue one, methane, the big contributor from livestock, and which of course mostly comes from livestock in agriculture. This shows you emissions, the way they're sort of conventionally compared, and of course we don't really care about emissions. What we care about is the warming they cause. But that's a similar message if I look globally. If I look, global contributions to warming, you can see carbon dioxide's in front, methane's a close second, actually. It's about half of the warming caused by carbon dioxide is the warming caused by methane. So methane has caused a not insubstantial amount of warming so far. Nitrous oxide's a fairly distant third. But when we look at agriculture, methane is right out in front. So unless you understand how methane affects global temperature, you can't really get to grips with what we need to do about agriculture. And that's kind of where I come in, because we have done quite a lot of work on how we relate methane and carbon dioxide in climate policy. Again, can't emphasize enough, I'm talking here about the direct impact of agricultural emissions. We had a lecture several lectures ago on the carbon cycle and on offsets and on reforestation, deforestation, and so on. So that's a different topic, a very, very important one, but I'm just focusing here on the direct impact of agricultural emissions, which are dominated, as you can see from this figure, by methane. And, ruminant farmers, livestock farmers are understandably anxious, although I learned in researching this lecture that apparently there's been a published study saying that hugging a cow is good for anxiety, so maybe they're able to hug their cows. But it's understandable that ruminant farmers are anxious because ton for ton in the atmosphere, methane is an extremely powerful greenhouse gas. 100 times more powerful. You'll see numbers out there, all sorts of numbers out there, and I'll explain to you why it's possible to come up with lots of different numbers for how much more powerful it is than carbon dioxide, but it's definitely a lot more powerful, if you'll forgive the sort of rather approximate expression there, than carbon dioxide. And methane emissions are intrinsic to the way ruminants digest grass. It's like that, the ruminants rely on bacteria to break down lignin into sugars they can actually digest themselves. And a sort of side effect, an undesirable side effect of that process, of course, is that some of the carbon in the grass that the ruminants have eaten is converted into methane. Nobody really wants this. I don't know whether the cow does, but certainly the farmers don't, because it's wasted calories, if you think. The cow just belches out the calories rather than ingesting them. And there's lots of really interesting ideas and lots of research going on how the fraction of the calories in the grass that the cow eats can be, or sheep as well, like all ruminants, that the ruminant eats can be converted. And we'll talk about those, we'll mention those in the course of this lecture, but they come at a cost. It's definitely cheaper to let your cow just browse on grass and belch out methane. There's a lot of conversation, particularly in the farming community, about how much carbon soils absorb. And again, this is one of the things I'm not going to talk about. Sorry to disappoint anybody who's a soil enthusiast here. There's a lot of science to be done on it, but broadly speaking, it looks as though on a global scale, pastures can absorb, they can be managed to absorb enough carbon to compensate for perhaps livestock-related nitrous oxide emissions, but not enough to compensate for everything. So certainly not enough to compensate for the methane. So if we were to treat methane, as many people do, as some kind of super carbon dioxide, I often hear it referred to as a super pollutant. How can livestock farming, if it's intrinsic to livestock farming that you generate methane, and if you regard methane as this kind of super pollutant, then how can it ever be consistent with net zero? Well, okay, so this is where we get into what I'm trying to explain today, and I've been trying to explain to people ever since we started working on this back over 10 years ago now, when, and just as a little history to this, the original net zero papers, which all came out in 2009, talked about carbon dioxide. And understandably, sort of very quickly after those papers appeared, people said, well, what about methane? What have you got? What has the science got to say about the target for methane? Because the net zero papers basically showed that it wasn't enough to reduce carbon dioxide emissions 80% or whatever we were talking about at the time. They had to go all the way down to zero. So what we see in the latest scenarios that actually meet the goals of the Paris Agreement are that carbon dioxide emissions need to be reduced to net zero. That's the top panel you see behind me. And methane emissions are also reduced in these scenarios. But notice, that carbon dioxide goes all the way down to net zero in the green and blue, which are sort of 2 degree and 1.5 degree scenarios. That goes all the way down to zero, while the methane goes down by about 50% or so. Now, those methane reductions would reduce peak warming in the second half of the century, assuming we do actually do all the other things we need to do in order to stop the warming. They would reduce peak warming by 0.2 to 0.3 degrees. Now, that's really useful. I mean, there's no getting away from the fact that, yes, methane reductions are an enormous help in reducing peak warming, particularly assuming we actually do manage to stop the warming from carbon dioxide, it'll make a big difference to reduce methane as well. But just to people, I often hear the headline, methane's the most powerful lever we have to address climate change. It's like, well, wait a minute. Methane reductions would reduce peak warming by a couple of tenths of a degree. Meanwhile, the carbon dioxide reductions we're talking about needing would reduce the rate of warming, not the peak, but the rate of warming by 0.2 of a degree per decade. So if you'd like to put all this into context, the total amount, including energy-related methane emissions, the total sort of amount we can win by reducing methane emissions is, 1 to 2 decades worth of carbon dioxide-induced warming at the current rate. So don't let, particularly the fossil fuel industry is quite keen on talking about methane because they have some of them at least, have a bit of a positive story to tell about it. And they'd much rather talk about methane than they want to talk about CO2. So don't let anybody sort of distract you from the complexity of the methane issue into thinking that actually we don't need to worry about CO2. And the CO2 is the big one, and the one we do need to sort out. And we're going to talk about CO2 in the final lecture. But in this one, we do also need to talk about methane. Because one of the things you realize is that in these scenarios, these are success scenarios, these are scenarios where we do stop the warming around the middle of this century, but methane emissions don't go all the way to zero. They drop by about 50% or so, and then they stabilize again. So why not? Why don't they need to decline all the way to net zero? Well, the reason is, in many ways, ridiculously simple. There's a very important difference between methane and carbon dioxide, hinted at in this picture behind me. What comes out of the gas stove, of course, is methane, and methane burns. Okay? Unlike carbon dioxide, good luck to you trying to burn carbon dioxide. It's an annoyingly unreactive gas. Methane is a reactive gas. It doesn't burn technically in the atmosphere, but it oxidizes. If you put methane into the atmosphere, it does react with other species in the atmosphere and eventually is converted to carbon dioxide. But remember, we were saying that methane, a ton of methane in the atmosphere has a huge warming impact. If you convert that ton of methane into a ton of carbon dioxide, if you convert all the carbon in that methane into carbon dioxide, it only has the same amount of warming impact that the carbon dioxide, that amount of carbon dioxide has. So, unlike carbon dioxide, methane, the warming impact of methane doesn't accumulate in the climate system in the way that carbon dioxide does, which has been the sort of nub of the lectures of the past 3 years. I probably lost count of the number of times I've banged onto you about the fact that carbon dioxide accumulates in the climate system, and therefore the only way to stop carbon dioxide from causing further global warming is to reduce carbon dioxide emissions to net zero. The same does not apply to methane. So if we just, think about, just to explain this with some very simple schematics of what happens when you switch on a source of carbon dioxide. Imagine the world sort of suddenly switched on emissions in year 1 and then emitted at a constant rate. So that's my emissions over on the left. What happens to the concentration of carbon dioxide in the atmosphere and its impact on the global energy budget, on the imbalance in energy coming in from the sun and energy going back out into space, which is the nub of the climate issue. So it basically goes up in a straight line. Carbon dioxide accumulates. You switch it on, it just builds up in the atmosphere. That's what you can see that. There's just a little bit of a curve to it, but for the sake of argument, it's a straight line. So carbon dioxide accumulates. Methane behaves totally differently. First of all, notice the methane emissions I've plotted here. That isn't zero, although it's pretty close to the zero line. These are so-called carbon dioxide equivalent emissions. So we use an exchange rate between methane and carbon dioxide conventionally. So your government uses this exchange rate. 28 tons of carbon dioxide is equal to 1 ton of methane. So you can see those two emission lines are sort of notionally equivalent amounts of these two greenhouse gases. Even though there's much less of the methane one, methane's more powerful, so it gets upweighted by this 28-to-1 exchange rate. And that's every climate policy. When you work out your carbon footprint, the BBC calculator or whatever, they're all using this idea that methane is just equivalent, 1 ton of methane is just equivalent to 28 tons of CO2. So this is, although it sounds like a really sort of nerdy issue, the exchange rate between different greenhouse gases, it's very deeply embedded in everything we think about on the climate issue. So those are the emissions on the left. Now on the right is the impact of these emissions on concentrations expressed in terms of the energy imbalance caused by these changing concentrations in the atmosphere. And you can see, totally unlike the carbon dioxide line, methane shoots up and then levels off. Okay, so because you've increased the amount of methane, you've turned on the gas, so to speak. So there's more methane going into the atmosphere, but then it's because that extra methane in the atmosphere starts to oxidize, and so the overall rate of oxidation and burning of methane in the atmosphere goes up because there's just more methane there, and eventually they stabilize, and you end up with a constant but higher level of methane than you would have had otherwise. So it's a bit like back to the bathtub analogy, carbon dioxide works like the bath with the plug in, and you turn the tap on, bath fills up, the only way to stop it filling up is to turn the tap off. Methane works like a bath with the plug out. You turn the tap on, it fills up a bit until it's running out the plug at the same rate as it's flowing in from the tap. So their behavior is very different. By the way, you'll notice these two lines cross at exactly 100 years. And by the way, that's not a coincidence at all. That's how we conventionally choose this exchange rate. So that's how they work out that 28. It's so that if you switch on a ton per year of the two gases, after 100 years, they have the same impact on the global energy budget. But you could choose a different number of years, of course, and people have lively arguments about how many years you should use to decide how to compare greenhouse gases. But what we really want to know about is not the impact on energy imbalance and concentrations, its impact on temperature. And that's a similar sort of picture. You can see here, again, the carbon dioxide line is even straighter. You put carbon dioxide into the atmosphere, it warms up the planet. That's the way carbon dioxide works. Methane warms up the planet quickly and then warms up the planet relatively slowly. So it's a different sort of profile. And this is where I'm going to ask you to concentrate very carefully. If you ask yourself the question, what carbon dioxide emissions would I need to give a temperature profile that looks like that blue line? Remember, we've been talking about equivalences between greenhouse gases. And the red line and the blue line over here are very obviously not equivalent. They don't look like each other. So what could I do to my carbon dioxide emissions to reproduce, to behave more like the methane? Well, I obviously need more carbon dioxide to start with, and then less later to get the right slope. Indeed, we can put some numbers on that. It looks kind of like this. Yes, it's not a great fit. Yeah, that's a bit of a wiggle there. We could probably fix that. But this is really just an illustration of the point. It's not really, we're not trying to reproduce the methane behavior precisely. We're trying to capture the essence of the way the climate system responds to methane emissions. And so if you want to know how the climate system responds to a source of methane that you switch on and then keep at a higher level, you need to match that, you need a lot of carbon dioxide over a short period of time, about 4.5 times the factor of 28 that is conventionally used to draw an equivalence between carbon dioxide and methane. And then after 20 years or so, you can tone it down a lot. In fact, you can reduce it by a factor of about 3.5 or so. And that then reproduces, if you were to emit that amount of carbon dioxide, you then get a warming response that looks very like the methane response. Okay? So if you wanted to make a carbon dioxide emission that matches the methane response, that's what it looks like. So, and this is very well-established science. In the most recent report of the Intergovernmental Panel on Climate Change, it was summed up by this sentence: expressing methane emissions as CO2 equivalent using that 100-year global warming potential exchange rate, that factor of 28, it overstates the effect of a constant methane emissions on global surface temperature by a factor of 3 to 4. That's the 3.5 I was talking about, the long-term one, while understating the effect of any new methane emission source by a factor of 4 to 5 over the 20 years following the introduction of a new source. I often complain, and if you're watching, please bear this in mind, farmers tend to stop reading at the comma of this sentence. And just read, they've overestimated it, I'm out of here, I don't need to worry about this. No, the second part of the sentence is very important too. Any new methane source causes a lot of warming, while a steady methane source, if you want to try and reproduce the impact of a steady methane source with CO2, but one which has been going for more than 20 years, you don't need nearly as much CO2 as the conventional exchange rate implies. To give you this in maths, the standard equivalence is to say that 1 ton of the emissions in carbon dioxide equivalent is just 28 times your emissions of tons of methane. So you take your tons of methane you emit in any given year, multiply by 28, and that's what DEFRA or any carbon footprint calculator will say your carbon dioxide equivalent emissions are. And that doesn't, as I hope I've convinced you, reproduce the warming impact of methane on global temperature. So instead, we can say, well, instead of multiplying all of the emissions by factor of 28, you multiply new emissions by a much bigger factor, 4.5 times bigger, and then you subtract the emissions from 20 years ago, multiplied by a bigger factor, but one which is quite close to 128. Okay, let me just bear with. Okay, let me just explain to you why this works. Okay, this does give you the right answer. If your emissions are unchanged, then you're subtracting the same emissions from 20 years ago as you have today. And so you're subtracting 128 minus 120 is only 8. That's 3.5 times smaller than the conventional exchange rate. That's the factor of 3.5. I'm just showing, this is just in numbers what I showed you already in the graphs. If your emissions have risen, you have to multiply the new emissions by a big factor. New methane causes lots of warming. And if your emissions have fallen by 6% over 20 years, so the 6% comes from 8 over 120, but basically about 3% per decade, then the amount of CO2 that you need to reproduce the temperature impact of your methane emissions over time is net zero. This is where farmers get very focused. Okay? Let's have a look at that. So back to that figure we had before. I'm just going to, so you can see it, I'm going to multiply the methane line by 100, okay? So you can see what's going on. And then we just make the methane, so instead of switching methane emissions on and keeping them constant, we allow them to decline at 3% per decade, okay? Halving over about 200 years. The result is you push up global temperatures and then they're flat. So provided methane emissions decline, global methane emissions decline at around 3% per decade, they don't cause any additional global warming. They don't undo the warming that you've already caused, so it doesn't mean they don't matter, but they don't cause additional warming in the way that additional carbon dioxide emissions do. So this is where it all gets quite philosophical. Are these equivalent? A closed power station caused warming in the past when it was running. It's closed now, so it's not causing warming anymore. A herd of cattle, I think this one's in Northern Ireland, it's gently declining, 3% per decade. It caused warming in the past when the herd was built up, but because methane emissions from the cattle herd are going down fast enough to balance the warming impact of their ongoing, because the decline is enough to balance the warming impact of the ongoing emissions, it's not causing any more warming. So many people, I hope we'll come back to this question. I hope you realize there's a question here. Are these equivalent? Yeah, there's a sense in which you could argue they are. There's also a sense in which, and I should stress, plenty of colleagues, people whose views I respect, absolutely, feel very strongly that you can't regard them as equivalent because the argument goes, you can undo the warming caused by the herd of cattle much more easily than you can undo the warming caused by the power station. The way it's often put to me is, yeah, but the power station operator is doing nothing, but the owner of the herd of cattle is maintaining the herd of cattle. They have new calves every year. They're keeping, if the owner of the herd of cattle did nothing, temperatures, their impact on global warming would fall. But this comes down to, what do you mean by doing nothing? The owner of the power station may have made a huge amount of money and retired to the Bahamas, and now they're doing nothing, so they've got no further responsibility to worry about all the warming they caused. Whereas if you tell a livestock farmer that leaving their livelihood and going and getting another job stacking shelves in Tesco's, that's doing nothing, they might not appreciate it. So it does come down to this question of what do we mean by doing nothing, which is actually quite a philosophical one. It's not something which we can really come up with a scientific answer to. But it doesn't mean we can't understand what's going on and then form our own views about what responsibilities different sectors have. This is all quite philosophical, quite abstract, but let me just sort of tell you why this matters potentially for the UK. So this is UK emissions in the conventional CO2 equivalent units, 1 tonne of methane, 28 tonnes of CO2. Notice that methane emissions have come down a lot since the 1980s. Our government's very fond of telling people that our emissions are down by a factor of 2 since 1990 or whatever. And a lot of that progress was actually achieved by reducing our methane emissions. It's something I don't think we should be too proud of, because some of you in the room may remember that this sort of thing was happening in the 1980s. This is a bungalow in Derbyshire that literally exploded one morning. Fortunately, nobody was killed, although 3 people were very badly hurt, because of methane leaking out of a nearby landfill. It wasn't even under the bungalow. It was about several hundred yards away, and it had leaked through the rock and got into the bungalow, and suddenly the whole thing blew up. Our landfill was completely out of control. And we did do something about it. We introduced landfill taxes. We got landfill methane under control. It's, so most of that, half of that methane reduction that the UK achieved was just by fixing landfill methane emissions, which were just inexcusable in the first place. So that they shouldn't have been happening. I don't think we should pride ourselves too much on the fact that we stopped doing something quite that stupid as having our rubbish tips blowing up our houses. There are other methane emissions, which, again, I think are just frankly inexcusable. This is a blowout in Kazakhstan quite recently, which was detected by satellite. They were drilling an experimental well. They found gas. They've actually found slightly more gas than they were expecting. And here's the gas just leaking out into the atmosphere. And that single incident would have actually been comparable to livestock emissions of several years just from the one well. That just shouldn't happen. And the industry, to be fair, does try to stop it happening, but they still quite often fail. So back to the UK emissions. So we talked about some of the, but we're focused on agriculture here because we've talked about those other sources which just need to be fixed. So if we blow up this panel to UK agriculture, so on the right is direct emissions from UK agriculture, and you'll notice that if you look at emissions in this, remember I've scaled up the scale so you can see the two. On the right-hand panel is a factor of 10 scale in the vertical, and if you compare these two, you'll notice that at the moment in 2020 or so. Agricultural emissions are, 10 to 12% of UK's emissions on this standard way of comparing greenhouse gases. And you'll often see that if you Google how much of UK emissions is due to agriculture. That's what Google AI will tell you, along with lots of other things, no doubt. So this is the sort of standard answer people have in their heads. But let's calculate the warming that these emissions have caused since the 19th century. Here it is. So carbon dioxide's caused most of our warming. Methane caused quite a lot of warming up until the 1980s, now declining again. If we look across at agriculture, you'll notice that, again, agriculture's contributed perhaps only 5% of the total warming due to UK emissions since the 19th century. Because so much of agriculture's emissions are methane, and because there isn't a one-to-one mapping between methane emissions and the warming methane causes. So what's the right answer for agriculture's contribution to UK's emissions? 10%? 5%? Or if we zoom in on the period since 1990, so I'm just saying how much has temperatures changed due to emissions of carbon dioxide, methane, or nitrous oxide since 1990 in the UK, total economy-wide emissions on the left and agriculture's contributions on the right. Now you suddenly notice that, hang on a minute, agriculture actually hasn't caused any warming since 2005. And so this is where farmers get, understandably, a little exercised. They appear to be being blamed for warming they're not causing. They are still contributing to changes that are going on in the atmosphere, because you'll notice the green line's going up. Nitrous oxide is still causing warming. The blue line is coming down because methane emissions, particularly from agriculture, are falling, have been falling for decades. The reasons, of course, if we just go back to the previous slide to see the agricultural methane emissions, notice how we had a sort of sharp drop in methane emissions around 2000. That was the foot and mouth crisis. Well, BSE followed in rapid succession by the foot and mouth crisis big contraction in the UK herd. So what is agriculture responsible for? So many farmers look at this and say, well, nothing. We're out of here. We don't need to worry about this. But then, wait a minute, because if we were to have eliminated UK agricultural emissions completely, not necessarily by eliminating UK agriculture, by the way, because as I said, there are other ways of reducing methane emissions than eliminating agriculture. But suppose we had done that, as just a thought experiment, back in 2000, we'd have seen temperatures drop quite rapidly. We'd have seen, well, not globally, because of course other countries are still puffing out greenhouse gases, but we'd have seen the UK's contribution to global, certainly the contribution from UK agriculture to global temperatures drop quite rapidly. Although, to put this into context, the amount of warming we would save by eliminating agricultural emissions would, at the current rate of progress, only amount to a decade or two of the warming caused by carbon dioxide emissions from other sectors. So, before you chuck agriculture under the bus, just remember that, to keep it in context, other sectors are doing plenty of warming as well. So, are these equivalent? Well, I hope we'll come back to that in the questions, but let me sort of, give you some things to think about, and what we might call a tale of two farms. Let's start with an arable farm, which was created by clearing some land of forest back before the 20th century. Then through the 20th century, it was farmed industrially, lots of nitrous oxide emissions, lots of soil carbon emissions as well, probably. And then in the 21st century, they've decided to lean into the whole net zero agenda, and they're doing afforestation and rewilding and so on. So what's this farm done over its history? Well, let's think about its warming impact. Before the 20th century, it caused a lot of warming because that deforestation released a lot of carbon into the atmosphere. While the farm was being run, those nitrous oxide emissions would have been continuing to cause warming through the 20th century. And now, of course, carbon is being reabsorbed by the farm through rewilding and reforestation. So that's the overall profile. Notice the line's not gone all the way back down to where it started because, the nitrous oxide is still out there, and it's unusual that you can put back all the carbon that you released when you deforested the farm in the first place. Now let's think of a livestock farm. Now, just as a thought experiment, to show you why this sort of is potentially an issue for livestock farmers. Before the 20th century, we established the cattle herd, and let's, for the sake of argument, imagine that it was established on water meadows, so no deforestation occurred in order to establish this cattle herd. Now, there's plenty of cattle herds in the world for which that is absolutely not true. And where the only way the cattle herds are being expanded is by deforesting as well. During the 20th century, we maintained a stable herd, and now we're reducing methane emissions from the herd, either by reducing head count or by reducing the numbers of cows, or by technical innovation by different feedstocks and so on to reduce the amount of methane per cow. So obviously remember I pointed out to you, new methane emissions caused lots of warming. So increasing the herd caused a lot of warming back before the 20th century. Stable herd actually caused a moderate amount continued to cause warming, but not by as much as you would have thought if you just used the standard exchange rate. And now that methane emissions are declining, the warming is being reversed. And you could argue, well, the only reason the farmer is able to reverse the warming caused by his herd is because the herd is big in the first place. But the same argument goes for the arable farmer. The only reason they're able to reforest, to allow forests to regrow on their land, is because they took the trees off 200 years ago. So it's actually quite a similar situation. I've said management and technical innovation here rather than necessarily reducing the herd count, because there's lots of ways of reducing methane emissions. It doesn't necessarily require reducing the amount of cattle you have on the land. This is a plant called Asparagopsis taxiformis. It's a form of red seaweed, which if you feed it to cows does actually has been shown to cut their methane emissions by up to 80%. The problem is the cows don't really like it. And it's quite fun reading these articles about how they're reporting that the cows sort of selectively, you sort of have this vision of the cows sort of selectively sniffling around and sort of avoiding this stuff they're being fed. But I was just hearing from a friend who's come along that apparently you can, if you feed them molasses, you have a similar positive impact. And unsurprisingly, the cows are pretty keen on molasses. So there's many ideas out there for reducing methane emissions. Or you can go really high-tech and give them something called 3-nitrooxypropanol, which is very effective. It's also very expensive to keep dosing your cow with this stuff, and no doubt Bovaer would be very keen for you to do that. But these all come at a cost. You can't reduce methane emissions from ruminants without spending money. And of course, this is a time when farmers are under pressure, from all sorts of directions. So how can we, how should we best address UK agricultural emissions, given what we now understand about the way methane affects global temperature and the way other gases affect global temperature? So let's just as a fun game, let's imagine you've got a small farm, 100 cows. Each cow is producing 100 kilograms of methane per year, and we had a 50 pounds per ton of CO2. That's a little bit lower than it is at the moment across Europe. Ton of carbon dioxide equivalent carbon price. So if you did the sort of conventional thing of just saying we're going to charge everybody for their emissions, which is kind of what you might call the more sort of, I don't want to think about this, so we'll just apply the same rules to farmers as we apply to everybody else. And that's for policymakers who don't want to think about it, that tends to be their reaction. What happens? Well, there's sort of three farmers we're thinking about here. So we'll call her traditional Trish, who's just maintaining her herd, keeping it constant. She'd be paying £14,000 a year. And this is a small herd, that's a big hit. That's a significant amount of money that she'd be having to pay into an emission trading scheme or whatever if that was the carbon price. Intensive Ian is increasing his herd by 10%. He just pays a bit more, an extra 10%, because that's how it works. More methane emissions. And then we have Techno Ted, who's introducing 3-NOP and all the rest of it. He manages to reduce the methane emissions from his herd by 40%, so he pays less, but he still has to pay for the methane that his herd is still emitting. Now, what would happen, and this is just to show you that it does make a difference, if you thought in terms of a warming-based policy, that you sort of rewarded farmers for reducing their impact on global temperatures, penalized them for increasing their impact on global temperatures, that was the basis of your climate policy. Traditional Trish would only be paying £4,000 a year because, of course, it's now that lower rate appropriate to. I'm assuming that Trish started her herd a long time ago, so we don't need to worry about the initial 20 years thing. So she's only multiplying by a factor of 8, not a factor of 28, because that's what you need to capture the impact of a steady source of emissions. Intensive Ian, of course, gets clobbered because he's increasing his methane emissions, and any increase in methane emissions gets given a very high amount of weight if you want to actually capture their impact on global temperature. But the really interesting one is Techno Ted. He gets a payout because he's reduced his methane emissions, he's lowered global temperatures in the same way that he would have done if he'd planted up lots of trees and absorbed carbon dioxide from the atmosphere. And therefore, if you had a warming-based policy, he would actually get paid £23,000 a year for 20 years. After that, as the impact of that reduction has washed through, he's back to having to pay like traditional Trish going on into the future, but of course at a lower rate because he managed to reduce his methane emissions. So if you look at these two policies, which one is likely to be A, most acceptable to UK farmers, and B, most effective in reducing methane emissions? And I would say it's a no-brainer. It's that one. So why don't we even talk about this? That's the challenge. Because I've had many conversations with people at all levels of seniority in our DEFRA, and they've said, they pat me on, well, they sort of figuratively speaking, pat me on the head and say, yes, Myles, we know this is an obsession of yours, and show me to the door. There is, of course, there's many catches and many strong, and one of the questions which is often raised but if you were to switch climate policy to focus on warming outcomes rather than this traditional carbon dioxide equivalent emissions, would that be inherently unfair on developing countries? And this is a really important point, which was raised by some colleagues a few years ago. And it's true that most herds in the global north are stable or declining, and they have therefore a relatively low warming impact, because stable methane emissions has lower warming impact than the CO2 equivalent exchange rate would imply. And many herds in the global south are increasing. And that, of course, has a large warming impact. So using warming impact to compare the impact of herds in the global north and global south would seem to be discriminatory against herds in the global south. And of course, but if you think about it, there's an even larger warming impact to many of those herds in the global south if those increases are being associated with deforestation, which in many cases they are. So yes, we need to be cognizant of the potential for unfairness between countries, but do we really regard it as fair to offshore our livestock production to countries in the global south, given all the other damage it does? It's not obvious to me that that's necessarily a good outcome. Just before I stop, I have to emphasize there is one unfairness that absolutely has to be addressed. I've talked entirely about the production of meat. This is a map of consumption of meat, and you'll notice in some countries of the world, including our own, I think they've carefully chosen this color scale so that the UK just squeaks under the bar and doesn't look quite as bad as Argentina or the United States. But there are plenty of countries in the world where people eat more than their body weight of meat every year, and lots of other countries in the world where people eat much less than 10% of their body weight in meat every year. And in India, perhaps, that's because of cultural reasons and preference, but I used to live in Kenya, and I can assure you, people in Kenya do not eat meat because they don't want to eat meat. They don't eat meat because they can't afford it. And so, we do need to address the fact that we in the global north definitely eat more meat than is good for us, and there needs to be a great rebalancing towards countries in the global south when it comes to consumption. But it doesn't necessarily mean, therefore, that production that it's a good idea to follow. So it's a good idea to reduce your meat consumption for your own health, for the sake of the planet, and for the sake of fairness between peoples, absolutely. But by the way, when you do that, it's important not to fool yourself into thinking that thereby you've done your bit for climate change. I've gone vegan, so I don't need to worry about anything else I do. I just wanted to show you this figure, which always gets people thinking. It's from a master's thesis, which a physics master student did a few years ago. He decided, his name was Bill Wu, and for his master's thesis, he decided to do a life cycle analysis of Bill Wu. So he decided, well, what does a representative British consumer do over their lifetime? He regarded himself as a representative British consumer, and you'll notice that, and then broke it down by greenhouse gas. And then just because he was wondering whether he should go vegan at the time, he tried what happens if the British consumer goes vegan. And you can see that does have an impact, particularly on your methane emissions, the methane emissions associated with your consumption. But in the end, your legacy is your CO2. Bill was rather pessimistic. He only gave himself 80 years. He's a pretty healthy chap. I'm sure he'll make it longer than that. But the important thing is that we all go vegetarian eventually. And then the impact of the methane emissions associated with our diet is essentially washed out of the system as that methane burns in the atmosphere. But your legacy is your carbon dioxide. So, to come back, though, to agriculture and to production, I strongly believe, as I said at the beginning, this is not a fight we need to have. Because if we were to base climate policy on warming outcomes, I think it could be a win both for the livestock industry and for the planet. This lovely sheep in the west of Ireland is utterly unproductive. Livestock emissions globally are increasing, and that's causing a lot of warming. There's no question about it. We do have to take livestock emissions very seriously, but a lot of them are coming from animals like this one, which are essentially decorative. These Irish sheep, they don't need to be there. They do environmental damage. They're really not worth it. And apologies to any Irish sheep farmers that are watching, but it's true. There are huge variations in what we might call methane productivity, the amount of value that we actually get out of the methane produced by ruminant agriculture. If we were to reward farmers for reducing global temperatures through either carbon dioxide or methane, equally, that would massively increase the incentive to reduce and eliminate inefficient methane emissions. And it would also make it clear to our livestock farmers that there is a place for a sustainable livestock industry in a net zero world. So, to come back to our question, does net zero mean the end of livestock agriculture? I don't know where you've got to on this. I'm at, well, potentially yes, unless, and this is where you come in, you write to your MP to ask them why farmers' incentives are not based on their farm's warming impact. And if your MP gives you a long answer back, just say, well, it's global warming, isn't it? Isn't that the point? I hope there's some questions.